Happy Monday. Hope you guys all had a good weekend. So I've got quite an ambitious plan for today, as per my usual. So we're going to move into chapter 13 today. If you haven't already turned in your test corrections and your homework, you can do so at the end of class. Make sure that the test corrections are stapled. And if you haven't turned in homework 7 or 8, you should turn those in as well as with homework number 9 so that I can grade all of them. Okay. It is TBD as to whether or not I'm going to go through your test corrections, all problems, or if it will be a random sampling. I'm leaning in that direction because, well, like 3 homework sets and your test corrections to grade, and you're turning in your proposals on Wednesday as well. So it's a little bit much. But yes, so again, I will post. Will I post? Should I post an answer key to the test? Please. Okay, then I'll do that too. Okay, and homework answer keys should be available as of 2 minutes ago for like everything up until now. Okay, so all right. So just a quick reminder: gift of numbers proposals due on Wednesday. The actual event Tuesday. So 2 weeks basically, 4 to 6:15. So you should have by now already found a partner, and if you had to make special arrangements, you should have already done that as well. So if any of that sounds weird to you, then you should probably be talking to me. Okay, so the mathematics of the day. Okay, so algebra, right, is the language that we use to describe quantitative relationships, okay? And so we can represent relationships in a lot of different ways. So far we've already seen a lot of different ways. Can you guys tell me some of the ways that we've represented relationships between quantities? I'm sorry? We used ratios, okay. So ratios allowed us to capture like one snapshot of information, okay. So is there sort of like formats that we've looked at multiple pieces of information about one relationship? Does this question make sense? No. So my question is, what are the different ways that we've represented relationships between quantities so far? Like, what are the ways that you've seen information presented in this class? Yeah. Stories, absolutely, yeah. Okay, so we've had stories to describe context, okay. We've also had equations, yeah, to capture relationships. And we usually built those equations by starting with tables, right? Tables of data points, okay? So tables of ordered pairs were sort of the formats in which we presented information that was easy to recognize patterns from. Bless you. And story problems gave us context, and equations helped us represent these relationships in full generality, right? But there's another way to represent relationships that we haven't dealt with yet, and that is graphical representations. Okay, so we can use graphs to represent or describe quantitative relationships in a pictorial manner, right? So that we can examine changes in quantities and how quantities change together. So just a reminder, right? We're imagining that 2 quantities are related when each value of one quantity corresponds to a value or values of another quantity. Okay, so in the case where each value of one quantity corresponds to exactly one value of the other, what did we call that? I'm sorry? A function, okay? So in the case where I cross out the or values and I just leave, each value of one quantity corresponds to a value of another quantity, that was what we called a function. Okay? Okay, so what constitutes a quantitative analysis of a problem situation? Okay, so what I just said was that graphs allow us to like pictorially look at situations, right? But like, just what does it mean to quote look at a situation, right? Well, one thing that I'd like to highlight once again, if I haven't done a good enough job this far, is that this quantitative approach to problem solving is more than just thinking about problem situations in real world contexts, right? Like that's not the be all end all. Yes, oftentimes the problems that we're looking at are embedded in quote real world situations, but the quantitative approach is more about highlighting the ways in which the quantities relate to each other. Okay, so exploring those relationships that link quantities and the ways in which they change in tandem. So sort of to give you a perspective on like what this means, I'm going to give you a non-quantitative approach to exploring a situation and a quantitative approach. Okay, so here's the non-quantitative approach. So we're thinking about a car traveling at a constant speed of 55 miles per hour. A non-quantitative or strictly numerical like way of thinking about this situation, well, okay, can kind of stem from the questions that you ask. So you might ask a student to find the distance traveled if the car travels for 2.5 hours, and then ask them to find the travel time if the car travels 220 miles. These are very reasonable questions to ask about the situation. But notice that they instantly take the student away from thinking about the entire situation as a whole, and instead focus the student's attention on two isolated incidences within the context as a whole, right? So instead of thinking about a car driving along at 55 miles per hour for some duration, and that's like that, I've got that movie roll happening, right, in my brain. Instead of all of that happening, instead I'm taking a picture and thinking about what happened at 2.5 hours and what happened at 220 miles, okay? Instead of thinking about the whole picture at large, okay? And so what are students going to do in order to answer these questions? Well, very natural things, right? They're going to probably draw upon a formula that they've been told at some point in their life, okay, where d is the distance traveled, r is the constant speed, and t is the travel time, so d equals rt, and they're going to substitute in values and solve for unknown values accordingly. Is this wrong? No. Totally legitimate way to do mathematics, okay? But it's not a quantitative approach because it does not highlight the relationships between distance, rate, and time. It just sort of assumes those relationships as given and proceeds sort of blindly following a formula, okay? So in contrast, so let me just maybe highlight what I was saying out loud, right? So a student would take this formula and say, okay, well, if I want to know how far the car has traveled in 2.5 hours, then I can just say d is equal to 55 times 2.5 without really thinking about the whole situation, right? Again, not saying that's wrong. The student will get the correct answer, okay? But they're not conceptualizing the relationship between distance, rate, and time in any sort of meaningful way. Okay, so in contrast, instead of just asking, well, how far does the car drive after 2.5 hours, you could ask the student explicitly to describe the relationship between distance traveled and travel time. Now you can still ask the same questions as before, but if you first ask for this relationship, now you're entering into the zone of a quantitative analysis. Okay? So what is the relationship between distance and time? If we know that a car is traveling at 55 miles per hour, what do we know? What does it mean to say that a car is traveling 55 miles per hour? not a trick question. Yeah.
For every hour, he will be traveling constant distance of 55 miles.
Okay, so for each hour, if he maintains that constant speed of 55 miles per hour, he will travel 55 miles. Yeah. That is a very valid interpretation of what it means to travel at 55 miles per hour. Now, can we take it further? So, okay, so if you know now for every hour traveled, he'll cover a distance of 55 miles. Could I say how many miles he covers in 2 hours? How would I think about that? Celine?
Well, if you can assume that he's going the same speed,
Yeah.
you can just double it.
Okay. So you're doubling the amount of miles because we doubled the amount of time, right? Okay, well, what if instead of doubling the time, I half the time? So how far does he travel in half an hour instead of 1 hour? Divide what by 2?
Divide the miles.
The number of miles he would cover in 1 mile by 2 to get the number of miles he would cover in half a mile, right? So this kind of thinking, I've written out some examples here. So changes in time produce changes in travel distance, right? So as time elapses, the car moves because the car is traveling at a constant speed of 55 miles per hour. This is like the first thing that we have to agree upon, right? And then for a change in travel time of 1 hour, the distance traveled increases by 55 miles. This is what Brandon told us, okay? Now if you travel for 2.5 hours, 2.5 hours is 2.5 times as large as 1 hour. So the distance traveled will be 2.5 times as large as what it would have been in 1 hour. So 2.5 times 55 gives you that number of miles. Okay. If you were to travel for 220 miles, well, that's 4 times larger than the number of miles that you would cover in 1 hour. So that means that you had to have been traveling for 4 times as many hours as 1 hour, right? So you can do this type of analysis without ever falling back to that formula, D equals RT. This is a quantitative approach. Does it feel different? Can you feel the qualitative difference between falling back on a formula and then reasoning through a relationship? Yeah? Okay. So teaching arithmetic and algebra using a quantitative approach means that you're helping your students get a feeling for how quantities are related. Okay? So you could explore some relationships without ever referring to numbers. Because I have a different activity planned for us today, we're not going to do this one, but I wanted to highlight that there is an activity in the learning exercises that really highlights a way that you can do this with students using, creating your own pendulums, okay, and tracking relationships through that physical activity. Okay, so it's kind of cool, so make sure you take a look at that. We're going to do a different activity today, so hopefully you guys will think that one's just as cool. But in the case where you do wish to deal with numbers and capturing these relationships, with more support than just tables or equations or words, you can represent them visually through graphs, okay? And so that's what we're going to focus on today. So I actually have a scenario, okay, where a roller coaster ride is going to shoot people up and down and up and down and up and down. Have you guys ever seen these? If not, I have a video, so hang on. Wait for it. Wait, hold on. Do you see what just happened? Oh, sad. Go back to my video. We'll start it over again.
So this is the situation.
Okay. Any other quantities? How much time has elapsed from when the ride starts? Okay.
Alaska.
Any other quantities?
Finally, the search for brown bears begins. Denali Highway. Real.
So you guys already listed a good number of them, right? So you said the vertical distance from the ground, the amount of time elapsed, the speed of the roller coaster. Other things, did I miss something? How about the total distance that the roller coaster travels during the ride? That's a quantity, yeah? So a bunch of quantities are involved, okay? I would like you to focus on two in particular, okay? I'd like you to focus on the vertical distance of the people from the ground and the total distance covered by the ride, okay? And I'd like you to describe the relationship between those two quantities in words, and then I'd like you to try to construct a visual representation of the relationship between those quantities. Are there questions about the directions?
I think the vertical distance of the people that
Yeah, in the right.
are from the
From the
ground,
ground.
bottom of the ride over the top.
Yep. Well, to wherever they are.
Wherever they are. Okay.
So let's talk about it. We have this roller coaster, right? The roller coaster is moving up and down. The roller coaster is not the quantities that I asked you to analyze, though, okay? So when we think about the quantities that I asked you to analyze, vertical distance from the ground and total distance traveled, those are things that increase or decrease, okay? So when we talk about them, those are the words that we should be using, okay? The vertical distance does not go up or go down, okay? The roller coaster goes up and down. The vertical distance increases and decreases. What do you know about the total distance? Throughout the entire situation, what is happening to the total distance?
Increases.
It's always increasing, right? How can we think about that? Well, every time the vertical distance changes by +1, the total distance also changes by +1. It's really easy to think about if you think about that first upswing of the roller coaster. Okay? So as the roller coaster rises 1 foot, vertical distance increases by 1, total distance increases by 1. You can think about that happening for every foot as it climbs all the way to its maximum height. But then all of a sudden it changes directions, where the it is the roller coaster, right? So all of a sudden the roller coaster changes directions. And the roller coaster starts to fall. When the roller coaster falls 1 foot, what happens to the total distance? It still increases by 1 foot, okay? And you can walk your way through that until the roller coaster reaches its, dipping point before it changes directions again, okay? So if we think about that carefully, there's a couple of different ways that you could capture that information. And so as I was walking around, I saw a lot of your guys' pictures, because that took kind of like a really long time, I didn't have time for you to put them on the board. But some of the things that I saw from, why isn't my, hold on. Okay. So some of the things that I saw were people drew some axes and they put vertical, or no, what'd you put? Total distance on the horizontal axis and vertical distance on the vertical axis, presumably because you were sort of imagining that situation. Okay? And so what did we just say? As the total, as the vertical distance increases, the total distance increases by exactly the same amount. Okay? So if I increase vertical distance by 1, total distance will increase by 1. And I'll end up with something like that, right? Until the vertical distance achieves its maximum value. And then the roller coaster switches directions and the vertical distance begins to decrease. Now for every unit that the vertical distance decreases, the total distance increases by the same amount. Right? And then the roller coaster changes directions, so the vertical distance increases, total distance increases, etc., etc. Okay? So the thing that I'm trying to highlight in words is that if there's a change in vertical distance, a change in total distance here, if that's 5, guess what? This was a change in vertical distance of 5. And here, a change in the vertical distance of -3 corresponds to a change in total distance of +3. Okay? You really could be that specific in your graphical representation just by thinking through the quantities and the relationship between them, right? If your vertical distance changes by 6 feet, your total distance must change by 6 feet. It does not, you don't stretch the space-time distance continuum, right? So if your vertical distance changes by 6 feet, your total distance changes by 6 feet. If your vertical distance changes by -5 feet, your total distance changes by +5 feet. Okay? Now, not everybody drew this picture. Some people drew a slightly different one, where they had vertical distance here and total distance here. And so their image looked something like that. Okay? Let me show you the pretty version. Okay? So here are 2 images that you guys actually constructed. Do they capture the relationship between vertical distance and total distance? Do both of these graphs represent the same relationship between vertical distance and total distance? Well, how would we have to think about the axes labeling on the left side? What should I label the horizontal axis here?
Vertical distance.
This is the vertical distance. And this is the total distance. How do you know? Brandon, how did you know?
It increases while decreasing.
Vertical distance is increasing, then decreasing, then increasing, then decreasing, then increasing, then decreasing, right? Whereas total distance is always increasing, right? When you look at this image, We just said total distance is always increasing in a situation. Just from our analysis, conceptualizing the quantities, right? And then over here, we've got total distance on the horizontal axis and vertical distance on the vertical axis. So the question again is, do these graphs both represent the same relationship between vertical distance and total distance? They do, right? Okay. So this is a reminder that there is not necessarily a unique way to use graphs, but no matter which way you do it, they should represent the same pieces of information. And again, the pieces of information that they're representing is that, total distance is always increasing, even as vertical distance both increases and decreases. Okay, and if we were to dig into the numbers on these graphs, then we could see equal changes in vertical distance yield, the same change in total distance as we go. Okay. If we wanted to connect this back to our conversation about function, are we seeing functional relationships in both of these graphs?
Yes.
You say yes, you say yes. You said that fairly confidently. So how come?
I think he knows the answer.
Gullet, why did you say yes?
So I guess your total distance. So you have two sets for your total distance. You use it as your input, and then you use one of them as the input and the other one as the output, and they both work even though you kind of like mess with them.
I've messed with the visual representation.
Yes.
This is true by changing the axes. So when you say yes, there is a function. Okay. The easiest way to defend your answer is to be more specific. I asked a vague question. I said, is a functional relationship present? Okay. You say yes. Okay. Well, if you're going to say yes, then you should be able to tell me which quantity is a function of which quantity. Okay? So looking at the right side, which quantity is a function of which quantity? Vertical distance is a function of total distance. Why?
Because when that increases, the total increases as well.
What's the definition of a function?
It's when you have when the input has to have a connection to the elements on the output.
Okay.
But only so each of the inputs have to have a connection with only one of the outputs.
Output.
Yes.
Okay, so for each value of total distance, how many corresponding values of vertical distance are there? So for each value of total distance, how many corresponding values of vertical distance are there? So if I'm looking at a total distance of, whatever this is, like 90 or something, how many corresponding values of vertical distance are there? 1. Right? When I'm looking at a total distance of, who knows, like 150, there's exactly 1 corresponding vertical distance, right? That same information is captured here, okay? So for each value of total distance, there's precisely 1 corresponding value of vertical distance, okay? So in both images, vertical distance is a function of total distance. Is total distance a function of vertical distance? So the question was, is, total distance a function of vertical distance?
Well, I don't think so.
You don't think so? Why not?
Because the total distance might reach the same, it might go to the same point. Oh no, actually that would make it one.
Shelby?
If the vertical distance is the input, then it would have the vertical distances that the total distance might go could end up being the same vertical distance as well. So total distance, you go up to a vertical distance of 20.
Vertical distance of 20.
In the beginning. So like that first 20.
Right there.
Right there.
Okay.
And that was the input, 20 was the input.
Thinking about vertical distance having a value of 20. Okay.
Then that input would have another total distance as the output. So that can't be a function.
Sounds right.
So you have to go back to.
Trying to say, but I can't figure out how to say it.
So okay, so here's the thing, guys, right? I asked the question like, is total distance a function of vertical distance? The first thing that should be popping into your brain is, what's the definition of a function? So that you can answer the question based on the definition, right? So the definition of a function says for every value of the input set, there is exactly one value, corresponding value in the output set, right? So when I asked this question the way I did, is total distance a function of vertical distance? I'm saying think of vertical distance values as your input set and total distance values as your output set, right? So pick an input value, okay? So here's a random input value, right? Because I'm thinking about vertical distance, right? So somewhere around there, okay? How many corresponding total distance values are there? 1, 2, 3, 4, 5, 6. Oh, we definitely violated.
Oh, the one that you use on graphs.
Well, so here's the vertical thing. Okay, so you just touched on a phrase that only Americans use, right? The vertical line test. So the vertical line test is this terrible thing that lets people forget what the definition is. Why does the vertical line test work?
Well, it would only work on that one.
It only works on that one. So what are the conventions under which the vertical line test works? What's different between this picture on the left and this picture on the right? So what's the difference? Well, if we're thinking about function, what are the key things involved in a function? Input set, output set, right? Where am I representing the input set and the output set in each of these graphs?
Oh, and it only has to correspond to one in each element. So
In-
since it touches more than one, it doesn't work.
Okay, so in this graph, I'm representing the input set on the horizontal axis, right? And the output set on the vertical axis. So when I pick one input value, and I imagine drawing a vertical line through that input value, it intersects the graph in more than one place, hence violating the, quote, vertical line test. But guess what? If you put your input on the vertical axis and the output on the horizontal axis, the vertical line test doesn't apply. Okay, you've changed the rules of the game. Okay, question?
Can you clarify for me how you decipher which one is the input and which one is the output in this situation, in this problem?
So in the original situation, there was no input and no output. There were two quantities that were related. The second I asked the question, is there a function?
Right.
Well, now I've introduced the notion that there could be a way to imagine one of these sets as the input set and one of them as the output. Now, just asking the question, is there a function, is too vague to tell you which one to think of in which way. Okay? So then I had to be more specific. Is total distance a function of vertical distance? That wording is A function of B, implies that B should be thought of as the input set, and A should be thought of as the output set.
So when you flip it.
So if I ask the question, is vertical distance a function of total distance?
And the vertical would then become output.
Then the vertical would be the output and the total would be the input.
So when we make the statement vertical distance is a function of total distance, the vertical is the output and the total distance is the input.
Yes. Very good. Deep conversations from just one roller coaster ride, huh? This is great. Okay. Questions before I move us forward? Okay. Now, so there were some issues that just came up. We just had some really interesting conversations, right? So, okay, so both of these graphs do in fact represent the same relationship between the two quantities that we've been talking about. Okay, so even though they visually look different, they capture the same information. Now, there are some pros and cons to using one over the other, okay? And what you're going to see when you start teaching and using traditional textbooks is that usually people think about the horizontal axis as the input axis and the vertical axis as the output axis. This is a mathematical convention. If you take an econ class, they'll do it differently, okay? So I'm putting this big red warning down here that yes, we establish conventions in mathematics classrooms so that people don't have to like reorient themselves every time they look at a brand new graph. I would actually argue that it's better to mess with those every once in a while just to keep your kids on their toes, right? Because if you never deviate from these conventions, then students will start to do what we call shape thinking, where they'll look at the picture and they'll think it's a picture of the roller coaster actually moving up and down, for instance. That's not what we were showing. We were showing a relationship between vertical distance and total distance, which is very different than capturing a trace of a roller coaster rising and falling. Okay? So, when you think about capturing relationships, algebraically and graphically, there are conventions, right? So we tend to represent these things in a coordinate system. What's that? What constitutes a coordinate system? What are some of the subtleties that we have to be aware of? So on the back of your paper, I gave some of this information away by putting a picture. The picture I drew looks like this. And there's some tick marks with some numbers written next to them. Okay. So this image that I've just drawn, what am I capturing? Or what did I just draw? What are these things? What is this horizontal line with tick marks? Have you seen one of those before? Like, have you seen something like this before? That's a number line, right? Well, if I take this thing and I rotate it 90 degrees, have I changed the fact that it's a number line? No. Okay, so we create a coordinate plane by taking two number lines at a 90-degree angle. Okay. Now, convention dictates that we usually think about the same way we do with number lines, starting with negative numbers, right? And then increasing to positive numbers as we go from left to right, and then from bottom to top, right? Okay, so as I trace this horizontal number line from left to right, these values are increasing, okay? And as I trace the vertical line from bottom to top, the values are increasing. Okay. Well, these number lines, when you draw them this way, they create spaces. Right? They create different areas on this plane. So over here, where both the horizontal values and vertical values are positive, we call this quadrant 1. And then you travel, as you look counterclockwise, you get quadrant 2, quadrant 3, and quadrant 4. Okay? These are, again, just labels that we've all agreed upon as a mathematical community. Now, what did I say was special about quadrant 1? Both coordinates are positive. In quadrant 2, the first coordinate is negative, the second coordinate is positive. In quadrant 3, negative, negative. Quadrant 4, positive, negative. Okay? So what I just did was I captured a ton of information by using ordered pair structures where the first coordinate in that ordered pair is representing the value on the horizontal axis, and the second coordinate is representing the vertical value. So this plus minus in quadrant 4 is saying the horizontal values are positive and the vertical values are negative. So how would I go about graphing an ordered pair of 2, 3? So that's going to be in quadrant 1. And I should think about this 2 as a distance away from 0, right? So a distance away from 0 in the horizontal positive direction. So I start at 0 and I go 1, 2. And then the 3 I should think of as a vertical distance of 3. So 1, 2, 3. And it's an ordered pair because it's capturing that information simultaneously. So over, horizontal distance of 2, vertical distance of 3, and I can plot and label that point. Okay. What about negative 3, 0? So this is representing a horizontal distance 3 in the negative direction away from 0. Vertical change? None. Here's that ordered pair. Is that in a quadrant?
Is it okay to look at things like rise over run?
Hold on to that. We'll come back to that. Is the ordered pair negative 3, 0 in a quadrant? No. It's on the horizontal axis. Okay? So the quadrants are everything that's not on an axis as you move in any direction. Okay? How are we doing so far? Okay. So I heard you say it's on the x-axis. So there's a convention for you. Okay? Oftentimes in mathematics classes, we will call the horizontal axis the x-axis and the vertical axis the y-axis. Do we have to? No. And we should only call them these labels if those are the names of the variables that we're using to represent quantities, okay? So if you're using P and Q to represent the values of two quantities that you want to capture a relationship between, then I better not see X and Y here. I better see a P and a Q here, okay? Okay. Would it be wrong if a student labeled the vertical axis X and the horizontal axis Y? No, it's not wrong. It's just not conventional. Okay? So keep that in mind. That's a really fun thing to play with. Oh, I had this drawn out so that I could do that in a prettier way. But okay, so that was I was just gonna have the conversation I just had with a prettier image. Shoot, where are we at? 3:36. I have 14 minutes. I don't have enough time to do this. I have like 16 questions related to this one thing. This is the point that we're at, though, right? We're at this really rich place in the course where we've talked about quantities and relationships between them and how you can represent them with variables and equations and now graphs and tables. And oh my goodness, there's so much to do. Okay, so let's go back to the thing that I was just saying, actually, which is really kind of interesting. So if I were to ask you to graph y equals 3x. Is this too out of the blue, or does this mean something to you guys? Let's take a minute to figure out how we could graph the relationship captured by this equation.
Is it alright if I think, because I mean, these will try to kids y equals mx plus b, put it in that form, and then just go from there, if you know what that means.
Your kids won't know what that means.
Oh, okay. By the way, when is that brought in? Like, is that like 8th grade or?
That's usually middle school. So y equals 3x. What are we saying with this algebraic equation? What is this communicating? We have two quantities, right, that we're representing using x and y. And the value of y is always 3 times as large as the value of x. Okay? So if I'm thinking about how to capture that relationship graphically, I can do that in various ways. I could easily do that first by starting with a couple of points, right? So I could create a table of values. So when x is 0, for instance, what is y going to be? 3 times 0 is 0, okay? When x is 1, how large will y be? 3 times as large as 1 is 3, okay? When x is 2, how large will y be?
6.
When x is 2.34, how large will y be?
7.02.
Oh, that was fast. That's pretty good. I was just going to say this.
Oh.
3 times as large. Right? Okay? Negative values, you can do the same, right? Okay, so what each of these columns in this table represent are the relationship between values of x and values of y. Okay, so 2 pieces of information that we can now capture simultaneously using just one ordered pair, 1 point on a graph. Okay, so if we follow convention and we call this our x-axis and the vertical axis our y-axis, then 0, 0 corresponds to when both values have a 0 value, right? 1, 3 means a value of 1 for x, a value of 3 for y. 2, 6, 2.3 and some stuff, somewhere around there, right? Okay, -1, -3, -2, -6. Okay, so I've plotted a bunch of disjoint points so far, right? But could I talk about when x is 1/2 the corresponding value of y?
Yeah.
Certainly, right? What about when x is 0.75? Could I talk about the corresponding value of y? And 1.21 and 1.98 and 3.27, right? So for every value of x, I could describe the corresponding value of y. And I can capture that by drawing a continuous collection of points. Okay, so when I draw this line, this quote line, right, the way I'm really imagining it is a collection of infinitely many points. So many points that you literally cannot separate them, which is why they look like a line. Okay, so I could I wish I had a problem context to go with this. So what would be, my brain just went totally blank. I lost it. That's it. Oh, so what I was going to ask though is if a student were to not be accustomed to our conventions yet, and instead they labeled their axes so that this is the x-axis and this is the y-axis, could we still capture the same information? Yes, right? So when x is 0, y is still 0. And when x has a value of 1, y has a value of 3. And when x has a value of 2, y has a value of 6. Right?
Who would you like to text?
Why are you talking to me? That's the second time my phone has done that to me. Okay, so weird. You guys have to train me how to use my technology. It's really embarrassing. Okay, so we can still capture the same information. It might look visually different, right? But the same information is still there. So something we didn't have time to discuss today is like these scales that I've used here, both the x and y axes had the same scale, meaning one tick mark corresponds to 1 in each direction, but there's nothing that says that they always have to, okay? So you could construct a graph where your vertical axis is scaled by hundreds and your horizontal axis is only scaled by 1, for instance, okay? And your choice in doing so will depend entirely on what it is you're trying to capture, whether or not the values of the quantities get exceptionally large or exceptionally small. But remember that when you change the scales, sometimes your graphs will appear, it will change the appearance of the graph, right? And so people tend to have an association where they think about like steepness as being meaningful. So if a graph looks visually flat, that means something to people. Whereas if it looks visually steep, that means something else to people. But you can change that dynamic by changing the scales, okay? So when you look at a graph and you're trying to interpret, or when you're constructing a graph and trying to interpret what you're conveying, keep in mind, what are the quantities you're communicating about? What are the scales that you're going to use to represent the values of those quantities? And then what's the relationship that you're communicating? Okay? If you want to highlight a functional relationship, then it matters which axis you're treating as your input and output, right? Okay. So these are just issues and conventions to keep in mind. We're going to dig deeper into what Gullet brought up about this y equals mx plus b thing. We'll dig into that really deeply on Wednesday. Okay? Cool. All right, we'll stop there and So just a reminder, I have office hours, not now, because I changed them, right? So on Mondays they're before class, but tomorrow afternoon, Wednesday after class, Thursday afternoon, same here.
Is today's homework only going to cover what we did?